Okay, so this is a recap of the exercise of the example 2. Right, so we had the link. This is what I wanted you all to draw initially. So you show all your data, you represent all your data on one diagram. You have P1, P2, right? We assume what was the endurance limit because it was ductile, then we modified that value based on the actual material, the surface finish, etc. Right, so we have a modified endurance limit. We use the Goodman equation, right? So note we have KT over here, but because we don't have a stress concentration factor, there's no hole, etc. We keep the KT out, right? And we had N as equal to 1, so we really didn't need to put N here, but just for the sake of writing it, this is our sigma alternating and sigma mean, right? Because it's a tensile stress, right? All we have is a stress like this, so it'll be P1A, simple as that, what the stress is. So we have the max is P1, min is P2. Right, so we substitute the max and min into our sigma alternating and sigma mean equation and we simplify it. So we have alternating stress, then we have the mean stress. So now we could actually now substitute these terms into our Goodman equation. Right, so this was the sketch I wanted you all to do just to understand what the Goodman line is. Right, and as mean and the alternating stress plotted against each other. And all we have here is from Sn to S ultimate, there's our line. And we're saying anything that falls outside this line, between if we were to plot sigma mean versus sigma alternating, we say that we will have eventual failure or we will not have infinite life. Right? Remember, infinite life has to do with the endurance curve or the Sn curve. It might look something like this, and we see at about here, we have about 10 to the power 6 cycles. Right? This is your alternating stress here. Right? So we actually want to have approximately infinite life or about a million cycles. Right, so we substitute our sigma max, our sigma min into the Goodman equation, and then we just simplify. Remember, we have values for P1 and P2. We have values for Sn, we have S ultimate. Right, but again, we're keeping it in terms of parameters for now. Right, so then we could solve for A. Okay, A is our cross-sectional area, and once we get the area, then we could solve for the diameter. Right, so when you reach a simplified version, then we could actually substitute P1, P2, Sn, etc. So that's what we did here. Right, so we obtain and we actually solved for A. And once we get A, well then obviously we could solve for D. So that's our diameter. So this is our minimum diameter. Right, so we update the diagram. Okay, and we actually put our numbers. So if we were to substitute A back into our sigma max and sigma mean equations, right? So we come back to here, we had sigma alternating and sigma mean. Right, what I meant was sigma alternating and sigma mean, not max and min. Right, so we notice we have P1, P2, and then we have the A. So if we substitute A into these equations here, then we will actually get 39 for mean and 196 for alternating. Right, so when you plot that, it should be on the line because we solved the equation, so it actually is on the line. If it is, we had a factor safety n, well then the point would have been somewhere over here. Right, so the greater the factor the safety, the more towards this direction you're going, which means it's more safe, but at the same time it's a more bulky design. Right, so that is our fatigue design. The next question asks, what if we were to forget this whole fatigue thing and we say, okay, well, let us use the larger value P1. Let's use a factor safety of 2 and see how it compares. It should be safe or it might be safer, but let's just see. Right, so we're using the Tresca or the maximum shear stress theory. Right, it could be called this as our tau design, sigma yield on 2n. Right, and our maximum shear stress is given by this formula. Right, so our sigma x, as we say, is P on A. In this case, we're using P1 as the maximum value. There's no shear stress, there's no stress in the y direction. Right, so For safety, tau max must be less than tau design. So we substitute what x is, sigma x, sigma y, tau x, well, it is 0, it's 0. Right, so the equation breaks down to be very simple. Right, this is our tau design. So again, we could solve for A. Right, substitute our values, and we have A given there. Then we could solve for D. Right, so it's simple. And then you could automate these things in Excel. Right, so there's a little note here, considering fatigue and no factor of safety, the minimum diameter was 38.3. But if you were to consider static alone and forget about fatigue and you use a factor safety, even if you use a factor safety of 2, it's still less. Right, so what this shows is that if it is we design this thing and we say, okay, let's use a factor safety of 2, let us don't bother with fatigue calculation. Let's just use a factor safety of 2 and assume it to be static, we'll use a bigger load. So as an engineer, you make that decision. You come up with a diameter of 36.2, right? So it's okay, 36.2. Then we save. Let's just round it off to, let's just say we round off to 37. And we go ahead and we make this part, right? What this means is that in reality, factor of safety, the fatigue load, it will fail after some time. After a number of cycles, it's going to fail because the minimum allowable diameter was 38.3. Anything less than that, we're saying it's going to fail before infinite life or before a million cycles. Right? So if we use the static loading case or static assumption and we use a factor of safety of 2, it will eventually fail before a million cycles. And that is poor design. So this is why we need a factor. We need to consider fatigue. Imagine if we had used now a factor of safety of 2 in the fatigue calculation, then this would have been even larger, right? So it is a balance, and that is how using the different types of calculation you could actually fine-tune your design. And this is what makes a good design engineer. How you could take advantage of the assumptions and theories and calculations and analysis tools to kind of shave off weight and make a design more efficient. Right, so now that we have this, we could go on to example 3. If you have not done that already, then we could look at example assignment 2.